As an object is submerged in a fluid, it displaces a volume of fluid equal to the volume of the object. Gravity works on the displaced fluid in an attempt to restore the fluid to its original position. This results in an equal but opposite force that acts on the object. We call this upward force buoyancy. Looking at the equations, we see that the force of buoyancy is equal to the acceleration of gravity times the mass of the displaced fluid, which is found by multiplying the volume of the displaced fluid by the fluid's density. By taking into account the force of gravity acting on the object, we can derive the equation for the net force that acts on the object. Therefore, it can be seen that the net force acting on an object submerged in a fluid is equal to the acceleration due to gravity times the volume of the object times the difference in the densities of the fluid and the object. For our experiments, we decided to test the principle by varying the object's density and the fluid's density. We needed oil, water, rubbing alcohol, ping pong balls, salt, tape, beakers, a scale, a caliper, and a knife.
Using an X-Acto knife, take the ping pong ball and cut out a small circle and fill it approximately with 5 grams, 16.7 grams, 25.6 grams, and 38 grams of salt. After cutting the ping pong ball and filling it with sand, begin by cutting a long strip of duct tape and wrapping it around the ping pong ball, making sure to press down hard enough along the tape so that it fully adheres to the ball.
Next, place each ball on the scale and record their masses.
Using the ping pong balls, submerge each ball to the bottom of the beaker with marker and release.
To compare the densities between water and oil, we placed balls 4, 3, and 2 into the graduated cylinder. While not one of our experiments, this demonstration clearly shows the relationship between the densities of the objects and the fluids.
In order to find the net forces for each ball, we subbed our values into the principal equation F equals G V naught delta rho, making sure the proper conversions and calculations were made.
Based on the principle of buoyancy, the hypotheses of our experiments were, as the density of the fluid increases, the net force also increases, and as the density of the object increases, the net force decreases. Our experiments both visually and numerically support our hypotheses. We can see that as the density of the fluid increases, the net force also increases, and the data also shows that by increasing the density of the object alone, the net force decreases. Therefore, our experiments verify Archimedes' principle of buoyancy.
A practical application of Archimedes' principle can be seen in weather balloons. Weather balloons are used to transport sensors up into the atmosphere. These sensors, in turn, are beneficial in forecasting winter weather, severe storms, air pollution, and temperature forecasting. The mechanism behind a weather balloon is simple. By filling it with helium, or a gas that is less dense than air, the weather balloon will follow Archimedes' principle and thus float. This process can be illustrated conceptually by making the following assumptions and taking the following constants. Inputting these constants into the Archimedes equation, it can be seen that the net force on the balloon is pointed upwards. This indicates flotation.